Hello everyone, welcome back to the YouTube channel. You are watching Build AI with Sandeep. We are continuing our Transformer series. In today's video, we are going to break down an important part of the Transformer architecture, that is feed forward neural network, also called FFN or pointwise feed forward neural network. FFN or pointwise neural network. Today, we will understand what it is, why it is, how it works step by step. I will also show you a simple numerical example so that you will understand the flow clearly. So, what is feed-forward neural network? Inside every transformer layer, whether it is encoder block or decoder block, there are two main components. As you can see on my screen, there are two main components. First one is multi-head self-attention and the second one is feed-forward neural network. So FFN is a simple neural network that processes each token independently. That means if you have three words, each with vector size 3, FFN processes each vector one by one using the same weights. I'm again saying that using the same weight. I will tell you in the end of the video that why we use same weights. That is the secret that I want to share with you. In simple term, in simple term, feed forward network, feed forward network takes the output from multi-head self-attention. Multi-head self-attention applies two linear layer, then it applies non-linear transformation, and finally gives us a transformed output. So this transformation helped the model to capture complex patterns inside each token embedding. Now let's understand why we need feed-forward network. So self-attention is powerful, but it focuses on the relationship between the tokens. Feed-forward neural network is something different than the self-attention. Basically, a transformer also need to capture better semantics, also need to capture abstract feature. Let me write what transformer needs to capture. The first one is abstract features. Abstract features. The second thing is hidden patterns from each word. Third one is non-linear transformation. Fourth one is deeper representation inside each vector. So this is exactly what the feed-forward network do inside the transformer encoder and decoder. Basically, feed-forward network, you can think of it like this: that attention is helping in finding the relationship between the tokens, and a feed-forward network gives us a deeper representation of each vector. It tries to extract some complex pattern from each feature. So feed forward network help the model capture better semantics help to capture richer richer meaning of each word, better expressive features. Now, now let's understand why how the feed forward network works. So till now we understand what is feed forward network, that it is capturing complex pattern from each word, and why we need, because we want something that self attention cannot do. Self attention helps us to find the relationship between the word, but feed forward network help the model to capture better semantics, better richer representation of each word. Okay, and now let's understand how feed forward network work. So this is traditional neural network that everyone must know. I hope you all must be aware about this neural network, that these circles are neurons. Okay, and there are three layers: input layer that hold the input vectors, the second layer, this layer is basically a hidden layer, and this is output layer. So when, let's suppose we have embeddings, like we have a vector point 1, point 3, and point 4. Okay, this is our input, this is our input. So we pass one value to one neuron that hold this value and send it to the next layer, that is hidden layer. And hidden layer does the two things. Hidden layer does the two things that I'm going to explain to you. And after processing, it will, the output of hidden layer will send to the final layer, that is output layer, and it gives us output. So I took random values for the output, but this is what is happening inside the feed forward neural network. I will explain you in super simple way. Just give me 2 minutes. First, I want to tell you what are the two things that is happening inside each neuron of hidden layer. Okay, so what are the two things, two operations we can say. So first operation is in hidden layer, multiplying by weights, multiply by weights, and addition of bias, addition of bias. So let's suppose x1 is our input, one value. Okay, so first multiplying with weight. This is a random weight learnable parameter that will adjust during back propagation, during training of the model, and we add bias into it. Okay, so this is the first operation that is happening, and the second operation is we apply activation function onto this value. So apply activation function. And what are the activation function? So activation functions are nothing but introducing non-linearity into the neural network. Without activation function, neural networks are just linear transformation of matrix. Okay, linear transformation of matrix, and this is nothing, just linear transformation. We are multiplying and addition of random values that will not help us to capture complex patterns. So to get the richer representation of each vector, we need activation functions, and this is something where the magic happens. So activation function, there are different activation functions. We will we will we will talk about activation function in the further videos, but for now there is very famous activation function, that is ReLU, rectified linear unit activation function. And the formula of this activation function is max of 0 and x. Okay, so 0 and x, and the graph of this activation function is nothing but like this is a straight line. So it gives zero value for all negative values and positive value for all positive values. Okay, so we apply ReLU on this W1 X1 plus P1. So that's it. That's it. And that is what happening inside this hidden layer, inside each neuron in hidden layer. Okay. So we can write this neural network. We can all this since as we all know that in transformer architecture that everything is happening parallelly. Okay. So let me take you. I make a flow chart. I make a simple numerical example for you guys so that you can understand super simple way. Now on my screen that you can see that we were working on this flow chart and we were here. Okay, we are discussing this feed forward network. So inside this what is happening. So let me tell you. So I took this vector, and this is the output of layer normalization of word drink. So this vector is representing the word drink. Okay. So now in original research paper, this is the formula of feed forward network multiplying by weights addition of bias. Okay. So So let's take it like this, that this is input matrix, our X matrix. I make a random weight matrix for you to explain, and this is random bias. Okay. So first we multiply our input vector with the weight matrix. Okay. So now you can see that our weight matrix is of size 6 into 3. Okay. This is our W1. When we multiply this our input matrix, that is 3 into 1. Okay, so 3 got cancelled out and the output we will get is of size 6 into 1. It is of size 6 into 1. So this Z1 we will get after doing this operation. After that we multiplying this W1 X1 plus B1, then we will get our final Z1. Okay. Now the second operation, it is time to second operation, that we apply activation function ReLU, and the formula is simple, max of 0 and Z. So A1 is equal to sigma Z1, and it will give us this resulted vector. Again, now we have just applied activation function. Now it is time to multiply again with second weight matrix W2 and addition of bias. So this is our weight matrix. Now this is 6 into 1 and our weight matrix is what? And our weight matrix is what? 3 into 6. So this will gives us the final output vector of 3 into 1 size. Now let's talk about some important. Now I want to discuss two main things about this, about the feed forward network. Let me take you to the OneNote again. Have you realized that what is happening? What we just did? We did two things. We applies two linear layer. We applies two linear layer, and first layer is expanding. First layer is expanding the input network. Input vector is expanding the input vector, and second layer compresses the output of hidden layer. Now we are using two layers. First layer expands the input vector and second layer compresses the output vector of hidden layer. Now The first question is why feed forward network is pointwise is pointwise. So since feed forward network does not mix token information, each token is processed separately. Attention mixes token information. Feed forward network transform each token individually after the attention. So these separations help the transformer learn both relationship between tokens, attention, and meaning inside each token that it can be done using feed forward network. Now the second question is coming to the main part of this video. I said we use same weights. Now I can tell you why we use same weights. Inside the transformer feed forward network, every token position uses the exact same weight matrices W1 B1, W2 B2. Okay. So for example, token 1 uses W1 W2. Token 2 uses the same W1 W2 that we can see in our numerical example. Similarly, token 3 uses the same W1 W2. This is intentional, not a mistake. Let me explain why. Because FFN is pointwise and tokens are treated identically. In a transformer, we want the model to treat every position in the sentence the same way. Example sentence, cat drink milk. We do not want that one FFN only for the first word, another FFN only for the second word, another FFN only for the third word. Don't confuse with this concept that there are separate FFNs for each word. No, there is only one FFN that processes each token one by one. Okay, so when we do the matrix multiplication, that operations can be parallelized. Okay, we use input vector. We use previously in our example, we use input vector, one input vector that have three values. But if we use input matrix of 3 into 3 size, then also we can do the whole operations of feed forward network. So it is parallel. So So if we use multiple feed forward network, that would explode the number of parameter, makes the model overfit, make training impossible for long sequences. Instead, the transformer says all tokens should pass through the same feed forward transformation. This guarantees consistency, parameter efficiency, better generalization. So same weights for all token is the design. And one last thing, that why sharing weights is good, because the model learn a universal transformation that works for any token vector. This is similar to transformer share FFN weight across all tokens. It makes the model smaller, faster, more stable, better at generalization. So I hope you all understands the whole concept of feed forward network. If you like the video, then please do hit the like button and share with your AI friends, and don't forget to subscribe. In last video, the response was not so good, but in this video, I hope my video will reach to the 100 views, at least 100 views, since my channel is new. So that gives me motivation, and in future I will be coming up with more AI videos. And after completing the transformer architecture, I have few surprises for you to start. And so happy learning, guys, from my side. Thank you so much for watching my video again.